Today we'll be running a transient thermal phase change analysis on an ice cube to see how long it takes to completely freeze in the freezer. We'll begin creating our simulation files in the Simcenter thermal environment. We'll select all bodies since we only have the one ice cube, and our analysis type will be thermal. Next we'll create our new thermal solution. And we'll go through all of the items starting with the solution details. Here we can specify our run directory, and our solution type will be transient. Here we can see the advanced and parallel processing options. Solution units, will leave those as the current part. Our ambient fluid and radiative environment temperatures will set both to 10 degrees. And our gravity vector, here we can see it's currently set to positive ZC, and we can see that's correct based on the orientation of our ice cube. Here our initial temperature, we'll leave that as automatic. We're not going to perform a restart or set any heater controls. So we'll go to our transient setup, and this is where we'll specify our start and end time. And we'll set that at 2400 seconds. For our time integration control, we're going to set that to automatic. So it will decide what time step it needs in order to maintain the specified temperature tolerance of 0.5 degree Fahrenheit. And here we can also specify a minimum and maximum step for it to use based on that temperature error tolerance. Then we can specify at what interval we'd like to sample our results. All right, and lastly, for our results options, we want phase change quality as well as temperatures. So to create our thermal model, we'll begin creating a mesh. Here we'll use the Hex Dominant Mesher, but a TET mesh would be fine as well. All right, now that we have our mesh, let's assign some physical properties. We'll do that by editing the collector. And since we don't have any materials assigned to the CAD body, we'll go ahead and create one, because the water that's in the library does not include all of the phase change properties that we'll need. So we'll create a new isotropic material. We'll call it water phase change. We'll put in a mass density of 1,000 kilograms per cubic meter. Then we'll specify our thermal conductivity as a field. This will be a temperature-dependent field where we'll specify the thermal conductivity for solid water as ice, starting at 0 degrees Fahrenheit, with 2.2 watts per meter degree Kelvin. Then we'll continue with specifying the thermal conductivity for the liquid water as well at 0.58 watts per meter degree Kelvin. Here, once we've created that field, we can plot it to see what the value is as a function of temperature. All right, so that looks good. Next, we'll assign a specific heat. And this will be the specific heat below the phase change temperature, so for solid water or ice. Next we'll put in latent heat. Make sure we get the units right on that. Next we'll specify our phase change temperature and phase change temperature range, and then our specific heat above our phase change temperature. All right, so that looks good. Here, if we'd like, we can also rename the collector to specify what material the meshes have assigned to them. Alright, next we'll go to the sim, where we'll specify first our convection to environment, and we're going to specify two different values for convection to environment. The first is going to be on where the ice cube tray is, so we're going to select all of the faces and then hold down the shift key to deselect the top face of the cube. And here we'll specify 80 watts per meter squared degree Kelvin. And that will be going to our fluid ambient temperature, which we had specified earlier as 10 degrees Fahrenheit. Then we'll specify a slightly higher convection coefficient for the surface of the ice cube. Alright, next we'll specify our radiation. And here we don't need to specify any selection of bodies because it will be applied to all objects in the analysis. And then lastly, we'll create an initial condition, which will specify the temperature of the water as we're putting it into the ice cube tray. And we'll set that as 50 degrees Fahrenheit. Now we're ready to solve, and here I'll be periodically pausing the video, but I would like to show the solution monitor so we can see the evolution of temperatures in the cube. And here you can see it ends up pretty much all at 10 degrees Fahrenheit. And it takes a little under a minute to run. So let's take a look at our results. First we'll look at our temperature results. And we'll look at our temperature elemental. And we'll also turn off our shell mesh, which got created for our convection boundary condition. So here we're just looking at the solid element temperatures. And we'll also take a section cut through the ice cube so we can see what's going on inside. Alright, now we'll animate the temperature results across iterations. And you can see how the ice cube cools off and then completely freezes. And it's a little bit easier to see on the second run because the legend will stay consistent. So you can see pretty much the entire ice cube goes to pretty much freezing temperature and remains there while its quality is changing and the ice is forming. Another way we can visualize that is by creating a graph across iterations of a few of the locations. So here I'm selecting elements near the center of the ice cube. And we can see how the temperature drops close to freezing, and then as the quality changes, the temperature remains constant. You can see the curve of the blue dropping first, which is closer to the outside of the cube, whereas the ones towards the center take a little bit longer. Alright, and lastly we'll take a look at the quality across iterations. So here we can see the progression of the phase change from liquid to solid. Simcenter 3D Transient Thermal Phase Change Analysis helps you to predict the complex thermal performance of your parts.